Tonight's Western Joint Branch technical lecture on energy efficient shipping. Just a few parish notices before we begin tonight. Well, one parish notice. We'd like to put a call out to see if any of our Western Joint Branch members would like to be volunteer to become a PRI assessor. So the PRI assessors help in the local branch area by conducting chartership interviews for both RENA and IMarEST. There's a little short distance learning course you can do to become qualified for this. So if this is something you're interested in and would like to give back to the local branch community, please contact the secretary email address and we'll get all the details to you. And just before we introduce tonight's speaker, I'd also like to welcome the relatively new chairman, or chief executive, sorry, of the IMarEST, Gwyn Lewis, to say a quick hello. So over to you, Gwyn.
Yeah, thank you very much, Kevin, and a very quick hello to all of you. Given the current times and the circumstances, I've probably not had the opportunity of meeting many of you in person. There's been very serious restrictions in terms of the office availability and access. But hopefully I've met some of you through the activities of various committees or on the Fellows event that was held a week ago. It's a great privilege and honour for me to be your chief executive, and 5 months in, I'm starting to get to grips a little bit with the role. Just coincidentally, one of the things that Kevin just mentioned in terms of volunteers becoming a PRI assessor, that's a really important activity that we undertake for our members, and it's a really tremendous and very much appreciated role that you can do to also help the Institute and our future members in their career progression. Later this month, we'll be reaching out to all of our members with the annual survey. This month, the plan is that we'll go out in a little bit more detail with some of the questions, really trying to understand what you as members like in terms of what we do and the benefits we provide, and also get some ideas towards some future changes and the direction that you'd like to see us go. So please, when you see the email hit your inbox, do take the time to give us your feedback, either then or at any time. Please feel free to contact me directly with any comments, suggestions, or queries. And really, that's all I wanted to say. We're your institute. We work on your behalf. So let us know what we're doing right and also the things that we can do to improve. And talking of improving, I think I better hand back over to Kevin, and we'll hear about energy efficiency. Thank you, Kevin.
Thanks very much for joining us tonight. Just before I introduce tonight's speaker, a reminder that you can ask questions throughout the lecture on the Slido site. The code tonight is #energy that you can use on Slido to post your questions. And as usual, if you see a question that you would like an answer to that's already been posted, just make sure you vote on that, and we'll try and take the most popular questions in the Q&A section at the end. So tonight's speaker is John Buckingham. John's the Chief Mechanical Engineer at BMT Defence and Security in Bath. John was the Chief Technologist for the ETI-funded Vessel Technology Assessment System, VTAS, project, which developed tools and methodologies for the analysis of ship propulsion systems. Since 1999, John's been involved in a range of studies to assess the utility of energy-saving technologies for the commercial and military marine sectors. His lecture tonight is titled Energy Efficient Shipping. So over to you, John.
Thank you, Kevin. And hello, everybody, especially those at the Western Joint Branch of RENA and the IMarEST, and those who are also joining us from other places. And tonight I'm going to go through a number of slides covering the general area of shipping, the areas where there's scope for energy efficiency, and then go into a bit more detail on energy saving technologies that are based on wind-based devices, and then finally look at some of the methods that we use to look at these ships and these technologies, and so that we identify the right technology for the ship and its voyages and its planned voyages going forwards. And what we've got here is just the only video in the presentation, but it shows a bit of vector analysis in terms of the top. We've got the wind, we've got the vector of the ship speed, we've got the joint apparent wind velocity, we've got the actual lift, and then we've got the drag, and then we've got the resultant thrust going forwards. So this is just a very small snapshot of the kind of analysis that we undertake to allow us to identify how these kind of wind-based devices can benefit ships. As Kevin's pointed out, I've been at BMT a little while now, and basically I've been involved with a wide range of analyses of ships and energy-saving technologies, as we call them, both for the commercial shipping and for the Royal Navy and other friendly navies. And I'd just like to point out that obviously I don't do all this by myself. I'm supported ably by colleagues from the Naval Architects Department, Jeremy and Kathy there. And also we've had Beth Story and Will Hopes who have been placement students from the University of Bath, as well as others in the actual VTAS team. I'll tell you a bit more about VTAS in a minute. But the other people who get involved with the studies that we do are these colleagues here. David Pearson has done a paper on Flettner rotors about 6 years ago, which is widely available on ResearchGate. And my other colleagues, Tim Hardy from BMT, is also involved with studies at the moment on asset leasing models and such like. The other three people there are from Black & Veatch, who are one of our partners, or our major partner in the VTAS team. So what do we do and why are we doing it? Well, basically, there's been an awful lot of studies in the UK, especially with low carbon shipping, then shipping in changing climates, where in the past 10, 15 years, there's been a lot of studies, analysis, papers looking at barriers to the introduction of devices that can save energy and reduce clearly the objective greenhouse gases, CO2 and others. And basically what we've found is, or what we believe fundamentally, is that it's now time to really turn this into action. It's not a technology problem. It's now a question of whether we use regulation, whether we use, whether there's sufficient economic reasons and obviously commercial, corporate, social responsibility reasons for ship owner operators and others and the stakeholders in this business to basically implement and integrate technologies that will reduce emissions from their ships. I'm not going to talk through the details of every slide, but I think you can see that we see the amount of papers and research, novel research, diminishing as basically the point is made and the evidence is there, and obviously there are, as you'll see, increasing ships with wind-based devices. And now we've got hope. It's all about how do we make unit production cost lower to make the payback periods reduced, and to make the units easier to put on and off, integrate and operate. So VTAS is all about us and BMT and Black & Veatch integrating technologies and methods, procedures and other elements to make the whole thing move forwards. This obviously isn't shipping being a worldwide operation, a very disparate number of types of owners and operations. There is no one size fits all, no one solution fits all. Basically, as you can see there, we're trying to be in the middle of a number of principal stakeholders, owners, operators, the people who can finance this as a new means of green funding. Obviously, there's greater number now of financial institutions and moving out of oil and gas and other sectors into shipping and green technologies as a whole, not just for shipping. And then, of course, on the right, there's the cargo owners and those who wish to have their cargo and produce moved by ship in a way that is more socially responsible. And clearly, those of you in the UK, you're going to be missing a bit of the panorama program tonight about the reason why we're doing all this, the fact that global warming and climate change are something that we now, once we've put COVID aside, we can recognise that is a much larger and imminent danger, and for many people is already an issue in terms of flooding and issues with literal inundation. So that's our objectives, and Black & Veatch and ourselves, we have a good a match in respect to the fact that BMT is a leading marine engineering and naval architecture company, both for shipping in commercial shipping, based in Southampton in the UK operation, and the naval engineering for the Royal Navy and other navies in Bath. So we offer quite a lot of analysis in terms of systems, not just propulsion, power analysis, and also, as you'll see, it's quite important to fundamentally understand the other systems relating to cooling and heating. Black & Veatch, world famous and American-based company with a large presence in the UK in terms of wastewater and other such installations. But in this particular project, they brought with them their knowledge of port infrastructure, LNG handling, and as you can see there, the way they have engaged with the large number of stakeholders that we spoke to when we were doing the ETI project. So the challenge is, one hand, to try to demonstrate to ship owner operators and others who are involved as stakeholders, basically why they should fit an EST, an energy saving technology, and if they were, what can they expect by way of benefits, and when will they get, as the usual question is, when is the payback? And so clearly the fact that we're having that kind of conversation shows it's not all just about greenhouse gas emission reductions, it's about doing something to save money. And one of the main challenges is to save money in a world where we have a lack of predictability, be it the American-Chinese trade war, be it COVID and the way that's impacted on trade, and also as other factors that in terms of the ability to borrow money and the funding and financial crises that COVID has led to, as well as just trade. So this has also led to the cost of marine fuel falling fundamentally, and therefore introducing measures to save fuel and therefore get a payback. If you have very low cost of fuel and you're saving 5–10% of that cost, clearly you're not saving as much money every year, and therefore the payback increases. So the other issue is CapEx. How do we understand better to fit equipment to ships? How can we retrofit ships in a way that's affordable? One of the big issues is that we don't have time. The IMO wants us to introduce a reduction of 40% to energy intensity by 2030. Fundamentally, that means we've got to do things to the ships we have, not just the ships that are being built. And actually, because of the trade situation, there isn't a big demand for new ships. So we really have to address existing ships and means to make them operate more efficiently. Now, clearly, we have had, since the 2008 global financial crisis, we've had slow steaming, and that has benefited many ways in terms of shipping and fuel consumption, but you can only go so slow. If you want to move so many units from China to Europe, if you go half as slow, half the speed, you need twice as many ships, and then you still have, because of the resistance and the power varies with the cube of speed, you may still make a saving, but fundamentally you've still got a massive issue with CapEx of that many ships and many more crew. So it isn't just a question of slow steaming, it is also an issue of CapEx and actually making best use of your assets. What do we try to do? We work with the ETI. They funded us to do a project which we started about 3–4 years ago, and we studied with the ETI and Black & Veatch for about 2 years to develop tools and methods, and more importantly, maybe insightful analysis to allow us to work out how best to get an uptake of EST. So we look at ship operations, we look at ship data from ships, the parametric data for the power and propulsion systems. We see how the ships are operated. What do they do? Many of them may be ferries, they may be charter-based, going from A to B and B to A, or they may be trading more generally. That's the fundamental part of what we do, but we've also been looking at alternative fuels. There's a paper that you can see at the bottom there, future fuels for commercial shipping, that I gave at the RENA conference earlier this year in person. And there is an awful large amount of scope for adapting the circular economy for shipping, where we could make better use of waste wood, waste plastic, and domestic household refuse, as they do in the States, to create fuels such as isobutanol, which can be used as drop-in fuels to help reduce the dependence on fossil fuels. They're not the ultimate answer. The ultimate answer is zero carbon fuels, electrofuels from green energy, ammonia, hydrogen, etc., methanol. Obviously, methanol still needs carbon, but fundamentally, these are considerations for the immediate situation, and many of these products are disposed of in a way that's not very efficient, so-called waste to energy, where a lot of them are just burnt for heat and not actually transformed through thermal hydrolysis to useful fuel. And lastly, but not leastly, we also work with those energy-saving technologies that the ETI funded. They funded Avid, a organic Rankine cycle company in the northeast of England. They sponsored Teambridge propellers to develop more efficient propellers. And they also part funded the installation of two 36-meter Flettner rotors on the Maersk Pelican, which was also obviously sponsored by Maersk and also Shell. So we generally categorize energy-saving technologies into three principal sectors: the wet, the warm, and the windy. So wet is hydrodynamic, whereby it's the fundamental where we try to make sure that the hull has less resistance, the propeller is more efficient, and therefore there's a lower power reduction on the shaft line. Warm is addressing really something that we're trying to make best use of the fact that internal combustion engines generate heat when operating. So we take heat from the either jacket water or charge air cooler or the exhaust gas to drive things like absorption chillers to make chilled water, or organic Rankine cycles to make electricity. But clearly, ideally, you reduce the load in the first place by having a lower resistance and a lower loading on the machinery. And what wind gives you at the bottom is the fact that you're using renewable energy at source directly on the water without using green fuels and things to fundamentally reduce the load on your machinery and therefore reduce the fuel consumption for propulsion. So that we've just got a little graphic here where obviously we're showing very simply the wind-based devices. You've got a kite and you've got wing sails, Flettner rotors, which I shall talk about in more detail, IMarEST ducts, pre-swirl ducts, devices on the engine for twin turbocharging, dropping out cylinders, and then obviously waste heat recovery for, as I said, organic Rankine cycles. I'm talking here generally about larger vessels, seagoing vessels, cargo, tanker vessels, and maybe container ships, although they're not very conveniently designed for wind-based devices. But fundamentally, I'm talking about solutions that don't involve batteries, hybrid batteries, because the energy and the size of the batteries for ocean-going journeys would be considerable. Even though I'm going to talk mostly about wind-based devices, I've got a listing here of major equipments and solutions, some of which have fallen out of favor. We used to have a Grim vane wheel on the QE2 liner many years ago, but it fell off. So there's no supply chain for those anymore, really. There's no demand, but propeller boss cap fins are popular, albeit they offer 1 or 2% at most. Again, I'm not going to go through all these, but you can see that they all collectively provide a benefit, but it is arguably better that the wind-based devices can offer the quickest way of reducing the emissions on a ship. So in short form, we model the ship's resistance. There's methods like Holtrop and Menon, or ideally we might put it through CFD analysis and work out the resistance that way. We model the propulsion system. We have the propeller KTKQ curves and the engine characteristics. And what we do, we seek to model our software model, mathematical model of the ship's power and propulsion with the data we get from real ships, ship data as I call it. We model the energy saving technologies either using first principles, using trigonometry and publish values for lift and drag, or we work with suppliers of energy saving devices and use their own coefficients. We've the principal wind-based energy saving devices we use are these three. More about those in a minute. But fundamentally what we're trying to do is to show in historical form that those past ship voyages that those ships undertook, what would happen if they'd had a different energy saving device on board? What fuel saving would they make, and therefore consequently what greenhouse gas saving would they make? Obviously the greenhouse, usually CO2 is about 3.1 times the fuel saved. So if you saved 1 ton of fuel, you'd save about 3.1 tons of CO2 emitted to the atmosphere. BMT and Black & Veatch are sensibly independent of manufacturing. We don't make anything. We're not owned by any company that makes things like Wärtsilä or Rolls-Royce or any of the others. So we can give our independent perspectives to people and stakeholders and obviously engage with them in a way that is confidential. Unfortunately, so much about the modeling with data is all about getting good data about ships and its cargo loads. The ship at sea will have a hull, a fouling on the hull form, which is difficult to identify. So we've got ways around that. And then the fundamental thing that we do is that we make sure we declare all our data up front so that it can be challenged. And obviously people can review the models and approaches we make. We have two models, static models and dynamic models. Basically, static models is where we look at the ship situation, every knot speed from 1 through to the top speed, with and without the energy saving device at different sea states. And we also consider all the different parametric data from the sea all the way through to the fuel. Dynamic is where we take the ship data, we analyze each time step, each increment of data, and then we work out using the location of the ship. We work out from various meteo sources. We use quite a lot the European Centre for Medium Range Weather Forecasting, their data offline, and there's numerous others. We add the weather data to the situation so we can then analyze that ship in that particular sea state with the wave height, wind, temperatures and such like to work out basically what the forces are on the ship. Much of the data, many ships of course today have fleet performance management software systems on them, captures the data either sampling every second or all the way through to say 5 minutes, where it may be a composite of process data for 1 second. We've worked with different ship owner operators treating each of these in their own way, in a way that allows us to interpret how best we can the performance of the ship and its behavior, more importantly. The 1 second data can be very challenging in other ways, because what you're essentially looking at is the behavior of the ship when it's pitching, rolling, and yawing and such like. So fundamentally, it does mean that you are, and obviously there is a dynamic component to that. The ship is accelerating forwards, up and down and around. So that's why the analysis is always to be interpreted very carefully, because fundamentally we're not doing a sea keeping model. We're actually trying to interpret data on a 1 second basis. And when you see that data varying considerably from 1 second to another, you also have to be mindful of just how good the sensors are. Meteorological data, very important. Humidity is important in terms of the density of the air. That's important for wind-based devices. And obviously the significant wave height is important so that we can try to understand better the added resistance in waves. We do a force balance on the hull, both obviously in terms of the loading on the, in this case it's a Flettner rotor, the forces due to the apparent wind, that's the wind based on the trig combination of the true wind plus the ship speed. And then we've got, as you can see, the drag due to the wind passing over the Flettner rotor and the lift component, and those two get combined to provide the actual thrust. And of course, you also get side force, and as that affects also the listing or the heeling of the ship as well. Now, as an example, I'm going to go through a project that we've done with a turbosail on a 61,000 deadweight bulker, but we also did, I'll also be showing you some Flettner rotor work on this as well. This is the kind of high-level project plan on how we address a project such as this. We've got a pretty good idea on what we do, one thing after the other. But I'm just going to talk about a little bit about the ones in red, really, so as we're limited for time. So the ship in mind is a 61,000 deadweight bulker, principal data points there. So clearly one of the things is we try to align the data we get from the ship data with our own model for hull, trop and men, and try to also analyze the hull form, basically using 3D modeling, CFD. Basically, we've used NumECA, but we're now BMT using ANSYS as well. And we obviously trial many different methods and software to address that. And we also identify from our database of hull forms that go back for over 50 years from when BMT was part of the British Ship Research Association and also tied up with the National Physical Laboratory in Teddington and Middlesex. At this stage, I'd like to introduce you to an important association that's fundamental to promoting the use of wind-based technical solutions, is the International Winship Association. And the gentleman there is Gavin Allwright, who is the secretary of that association, and those who follow LinkedIn and Twitter and others will be familiar with his insightful commentary on the situations we have in terms of getting such kit on board, getting the mindset of owners and operators round to realizing that obviously the most easiest renewable energy to use is that which is around the ship at all times. So you can see the website there as well. So Flettner rotors are being rolled out from several companies. There's the Fern Pollux has got one that's been developed by a German-Dutch company in terms of researching it. Obviously, as you can see, it's quite a large Flettner there for the vessel. The Viking Grace has got a Norse Power one, as you can see atop it, and also so has the Maersk Pelican has got some very large ones as well. You can't see the scale, but I think they're about 36 meters high. And then bottom right, you've got Afros. The MV Afros has got 4 wind rotors from Anemoy Technologies, Marine Technologies, based in London, and operating on the Afros. And if you can see that in the picture there, novel means for moving them so that you can access hatch covers and such like. So what is a Flettner rotor? Well, it's designed by Anton Flettner back in the 20s, and basically he looked at it for helping increase the lift on the wings, front wings of aircraft, but he also derived it for use for driving ships or his own private yacht. And what you can see there is the lift and drag coefficient. So we get as the velocity of the rotor goes up, we get to very high lift coefficients of about 10 using the area of that particular Flettner rotor. So what do? We've got a Flettner rotor model, fully trigonometrically wired up, considers all the power required to drive it, as well as the issues with the drag, and also issues about what speed you need to turn it to get the best benefits. Our own software called PTOL or VESDA, we've got 2 different types, which allows us to do the assessment based on the ship definition and the technology definition. David Pearson, he wrote a paper back in 2014, which is on ResearchGate, and you can look that up, and that gives you a very good idea of the kind of modeling we've done. We've improved the model a wee bit since then, but the fundamentals are the same. I talked about the forces due to the wind on the Flettner rotor, and also, of course, we consider the angle caused accentuated here. But more importantly, perhaps, if the ship is rolling, this kind of effect is minimized. And actually, we've heard that sometimes the forces due to the Flettner, just like in sailing on an ordinary sailboat, can dampen the roll motion. So that's not such a bad thing. But also at slow speeds in high winds, the Flettner, when it's running, can cause issues, moments around the center of buoyancy, and consequently the rudder angle may need to change, and we model that as well. We also, because of the manoeuvring in slow speeds, we've also considered the wind direction and the speed not in knots, and how the Flettner rotor may need to be modified in terms of its speed and direction, of course. Another wing design that was undertaken, over 40 years ago now, is the Ashington, designed by John Walker, the Walker Wingsails. And as you can see, they're essentially vertical aerofoils, which provide a lift in a much higher lift given compared to an ordinary sail. They were fitted on the Ashington, atop the bridge, the wheelhouse, and the master of the Ashington, which lives near Bath, who still I met a couple of months ago. He's always very positive about it and how beneficial they were for manoeuvring, for pulling away from the wall if the conditions are right. But clearly that company is no longer in existence. And basically the modern company that is taking up this, not necessarily exactly the same design, I hasten to say, but a company down near Southampton called Winship, which is also using technology from the America's Cup and other high technology yacht racing to try to bring this through to commercial shipping. I'd just like to draw your attention here to the issues that commercial shipping has with, especially bulkers and tankers, with fitting wind-based devices, is obviously the visibility from the bridge looking forwards. And that's something I'll talk about later. The turbo sail is the third technology I want to talk about. And basically it was a way of having a smaller sail using basically an egg-shaped profile, but also using a suction side and a small fin to basically give some lift. Now this was originally conceived by Jacques Cousteau and his son, and they fitted it to their yacht, the Alcyon, but it was never developed further. People more recently, like Hessini, have done papers recognizing that it has benefits. And fundamentally, a Dutch company called Econowind now have their own product called the Ventifoil, which is now being moved onto various vessels. So how does it work? Well, fundamentally, we're still trying to get the benefit of a higher pressure here and a lower pressure here. And the lower pressure is also enhanced by this suction area, which maintains the boundary layer around the edge of the, of the turbo sail, thus increasing the area of low pressure so that you get the biggest benefit around the egg shape. Here's the Lady Christina. You can see they're fitted here to the inside a container. They can be folded down and put in the container. This was very much a couple of years ago when they were developing the technology, improving it. And now it's fitted to a few more ships, and there's probably many more that they have in production. But these are just a few to give you an idea of how they're moving forward. And my colleague, a year in industry student that we had called Will Hopes, is giving a paper at next conference at RENA next year on wind-based devices, and he'll be talking a bit more about how the turbo sail has been modelled by PMT. The work we did looked at the issues of without suction, how we basically lose the connection around here, and then we've also looked at issues with obviously the end issues of losing the thrust at the ends, and obviously it's important to also have a deck when you're modelling these devices. If you actually have the suction, you have the boundary layer going further round, your lower pressure area is further round, and therefore you get a better overall performance. Again, this will all be in Will's paper that he's writing with David Pearson. In our early studies, we looked at the different angles of attack of the wind on the turbo sail, trying to work out what angle the turbo sail should be to point into the apparent wind direction. And so we did some work on that. This is just indicative data, but it was very important to try and work out for something that was relatively new, just how would we use it to our advantage. I talked about the issue with basically visibility from the bridge for coal regs, so that they have a requirement to see so many ship, I think it's 2-3 ship lengths ahead, but also there must be no more than 5 degrees blockage for plus or minus 10 degrees of the center line. So we have software which allows us to do a quick first pass on this, so we can look at these 4 Flettner rotors. Well, they could be Wingsails, they could be Turbosails, and to work out and make sure that there's no, we're not breaking the rules for blind sectors. I was speaking to Gavin earlier, and basically there are, even though there are these rules, there is flag states have scope to give some concessions based on whether it's a slight, they are only slightly exceeding the blind sector, but also they can also have some make decisions based on multiple cameras, multiple people on the bridge who are keeping watch, as long as that's obviously maintained, so that any, obviously given today most bridges are almost full beam, there's all kinds of ways of making sure that basically the navigation and the coal regs and such like are all meeting the necessary safety standards. Putting cameras and CCTV on the bow may require duplication, redundancy, and these are the kind of measures that are being addressed. Obviously, with autonomous shipping coming through, such measures have got to be introduced anyway. So hopefully some way forward can be agreed by all the different parties. You saw this plot at the very beginning with my short video. We have the basically the actual wind. You reference the ship, you subtract the ship speed to get the apparent wind, then you get the drag, you get the lift, and then you get the resultant, and that resultant has a component going forwards and a component going sideways. And then we also include the rudder effects as well. We look at in the static analysis, we look at the thrust at different polar angles from the ship. So this is obviously one side. So if the wind is coming from here, this is the actual thrust that we've got. So we can work out basically whether we've got a reasonable benefit from this particular installation or whether we need to have a bigger one. The thing about wind is it isn't always blowing everywhere and at the same time at the right speed that you might like and in the right direction. We've, using our Meteor data that we've accumulated, you can see here that even now, if you're going from San Francisco to Japan, you might take the northerly route and then the southerly route back. But clearly, if you're going with the wind on both routes, you're not getting the wind on your bow, or sorry, on your beam, which is where you get the biggest benefit. So not every route will be beneficial. And also it's worth noting that the velocities of winds, this is in August, so okay, it's a bit light down here because it's the summer, but nevertheless, even at sea, it's not always as windy as it could be. And if you're looking at 10 knots of wind, 10 to 15 knots wind most of the time on average, that's what you've got to design for, not the big wind. And here we have, again, just to show, basically, obviously we've got all the wind down here, but so much of the shipping comes from China, around Singapore, across the Indian Ocean, and up through Suez and the Med. And there isn't always that much wind. So it is difficult sometimes when you look at the retrospective analysis to show how many, to squeeze as much benefit out as possible. And actually, if you look at the data, probability data, you can see here in this plot, you can get an idea of the fact that 5 to 10 knots is the biggest area where you're going to get wind. And then, of course, only half the time it's going to be maybe on the port and starboard quarter. So these issues are important when you look at the routes for designing your equipment. Talked about the fact we have to estimate the resistance. We did so much time trying to work resistance out from first principles and empirical methods, but we've worked out another way to do it now. So what we looked at is these kind of technologies. Typically the Flettner rotor is ratio of 6 to 1 height to diameter, and then you can see the wing cells that we've got there. And I'm not going to go through these in detail, but fundamentally we then do the static analysis where we show the different loadings across the ship speed on average. So we're averaging around the benefits of the wind-based devices. So the red one basically is the mechanical drive, the baseline, and these other solutions here in different colors are the alternatives where we're getting benefits. And then up here, we also look at the issues, that the extra loading that you might have in your auxiliary engine due to turning the Flettner rotor or the suction device for the turbosail. And basically the wind device makes the effective resistance lower. That's the idea. This is shown for sea state 4. So clearly sea state 3 and 4, which is a good representative of the overall weighted average, shows that you do get benefits for these particular installations that we've shown, the Flettner rotor, the turbosail and the Walker wingsail. And when your propeller is more lightly loaded, generally the efficiency is better. So clearly it's much more, the propeller is more lightly loaded at lower speeds, and then you benefit from a more efficient propeller all the way through. Fuel consumption falls, of course, that's the whole idea. And relative fuel consumption can be, as you can see here, in this range for 10 to 15 knots, 10 to 15%. And that's, again, based on lots of assumptions about azimuth, fully averaged azimuth wind speed. And what we've got here is ship data results where we've shown basically in green is the actual data for the fuel consumption. And this is the fuel if you've got the Flettner rotor running to save on fuel. So clearly, sometimes it's not windy enough, you don't get a benefit, but when it does blow, you get these benefits. So it is very difficult to predict, and even retrospective analysis clearly doesn't predict the future. And there's more on this at the paper that we gave at RENA last year. So what is our method? How do we do it? Well, what we've worked out is we get the ship data from either the owner operator or other sources. We take the Met data from the European Centre for Medium Range Weather Forecasting, and then we basically work out the resistance back down the propeller shaft from the propeller shaft power speed using the propeller characteristics, and also our own knowledge of the thrust and wake factors. We then work out the thrust for that particular situation, that moment in time from the wind speed and direction, and then we reduce the resistance to work out what the engine and propeller would have seen had the Flettner rotor or whatever device was working. And then obviously we've got new data for the propeller and for the fuel loading, and obviously we have to work out the issues with the additional loads as necessary on the auxiliary engine. But it's important to consider the fact that when we get ship data and when we get data from test bed trials for engines, the fuel lowest calorific value can be varying, so that can give issues. So here we've got a main engine versus power, and you can see the data points from the ship data here, and you can see that at this low load, because it's going up slow steaming, we've got an offset, and that will turn up later in our modeling. The results show that we've got, the green is the actual ship behavior. I think it has a little spurt of speed in the middle of the night and then carries on again to clear out the soot. But then when we add the Flettner rotor, you can see that we're benefiting considerably in this particularly well-chosen example on the 21st of February 2018, where we've got a significant benefit. And as I say, the purple is the ship speed, so she's going along at about 9-10 knots. And this is the Flettner rotor speed, 300 RPM. Another kind of result is that we've got the apparent wind. This is near enough on the beam quarter, really good angle. We've got the model data here, and then we've got worked out the ship speed again. Here's the blip with the ship speed, and then we've got the basically thrust that is being provided overall. Shaft speed, so clearly the propeller's doing less work, so it can turn slower. And here you can see that just based on this analysis, it's operating in a lower speed. Obviously, ironically, the more you go slower, you've got to watch out for clearly no dead areas, no run areas due to shaft vibration. So there's a limit to just the benefits you can get. And in practice, it's likely that obviously they'd operate the shaft in a way that was consistent with the Flettner rotor, given that this is a kind of point-by-point data, but the ship itself has got inertia, and so this is indicative. Most importantly, the overall fuel consumption you can see here in black is with the Flettner rotor, and here in purple we've got, or pink, or is it magenta, we've got the model of the ship this is the ship data in red. So clearly we've got this offset due to the calorific value of the engine fuel, and so that's something that when we're doing modelling in detail, we align and make a bit more effort. So basically, I've shown you how we apply take the ship data, add the model, add the information about the operation of the ship. Obviously, that also includes its draft and other situation. We work out the loading, reduced loading on the propeller due to the Flettner rotor or other wind-based device. That gives us a reduced propeller load, and we can then work out the fuel consumption. All looking back at any fuel data, any retrospective ship operating data allows us to look forwards. And clearly, as I said, more and more operators have this data. We work in confidence with these people. We recognise that the data is valuable, both for charter parties and other stakeholders. So we work closely with people in confidence, and obviously that's a fundamental part of what we do. As a company that works with governments, anyway, government agencies, we're used to working in confidence with obviously computer systems that are protected and such like. So that's it. I've cantered through pretty quickly. I hope you've got a few questions. And as you can see at the bottom there, the VITAS has a website. So you can go and have a look there, and also send me questions or other inquiries if you so wish. So thanks for your kind attention.
Thank you very much, John. So yeah, if you'd like to ask a question, you can post it now on the Slido site. Just a reminder, the code to access it is #energy tonight. Or if you see a question you would like answered, feel free to vote on it. One from me to start, John. What's the typical payback period for these wind devices? And do they vary significantly? Is one much better than the other?
The payback question is always usually the first one. It is, I wouldn't say there is any usual payback period. Fundamentally, every application is different. The reason why we're in the business of ships anyway is that almost every ship is different. So, but once you start taking sister ships, doing different routes, different weather conditions, we find that we provide the information fundamentally on the kind of fuel savings you might expect. When you take those fuel savings over the course of a year, we might look at January, March, May, July, every other month, analyze that, look at the benefits, and then you've got to then factor in what the capex is, the cost of changing the ship, the cost of the fuel, and what that owner operator has in terms of fuel deal. It's very tricky, but fundamentally, it's between 5 to 10 years most of the time. But we can see that, as I said at the beginning, with the commoditization of products, the greater manufacturing of them, you've seen that Anemoy has got agreements with production in China and things like that, and obviously Norse Power will probably do the same. You'll see that the price of them will come down, and obviously that will help reduce the payback period. The main issue is the fact that when we were doing the VITAS project, we were trying to predict the price of fuel. I knew it was a mug's game, but we had to do it anyway. And guess what? We were miles out because of trade wars, COVID, and everything else. So, but the price of fuel is low. As fewer people, obviously, they're using better quality fuel now, low sulfur fuel. That, as other factors use less oil and such like around the world with greater renewable energy, arguably that it will be difficult for the price of fuel to go up and make. So we do, the point is to get people taking these may require regulation and more corporate social responsibility rather than the incentivization of saving money. What was the other question?
Great. So we've got a question from Paul Vosper, saying one of your early slides you talked about the kind of the wet, the warm, and the windy as areas of potential saving. What's the relative ranking between those three, do you think, in terms of where the saving lies?
Well, I mean, windy is first. The hydrodynamic features have been, long been, as you will know, the hydrodynamic features of, with the introduction of methods like such as CFD and over the past 20 years been massively beneficial in terms of understanding wake fields, the relationship between the propeller and the hull. The work at University of Southampton in terms of CFD, relationship again between those two, and other places as well around Europe and elsewhere. So fundamentally, hydrodynamics should be very well known. I have to say, there still seems to be, the naval architects still seem to be changing their mind every other year on whether we have a bulbous bow or not, or whether it's an axe bow or one of the others. So I'd say I don't think there's any clarity there, but so most of the hydrodynamics should be sorted, and then you get things like air lubrication, which of course I think is very valuable and important. And I think especially as ships are going slower, that facilitates wind. That really helps wind because the vectors all come better if the ship's going slower. If the ship air lubrication is better in the range of 5 to 12 knots and things, much better again because it's reducing the viscous component of friction. So I'd say the hydrodynamics, and then the third one, the warm. If you've got some ships, the Maersk 3E container ships, which are using steam. You've got massive investment there to recover the waste heat to reduce fuel consumption, and that's successful. But not all ships have the space, or not all companies have the capital budget to do that. And so I think that's third in terms of. And arguably, if you've got a nice efficient hull form, you've got air lubrication, you've got wind devices, the amount of loading on your engines may be such that the amount of waste heat you're making isn't that great. So certainly, I think the warm is third down the list.
Okay, perfect. Thanks for that. I've got a question from Neil Salter here asking, are the heat recovery devices that you can fit compatible with exhaust gas scrubbers? Can you have both? Yeah, good question.
As exhaust exhaust gas scrubbers usually cool the exhaust gas. So I think I'd be more concerned about the NOx and the SCR devices, which do need to have a minimum temperature to operate at. But no, I mean, you used to have economizers. We used to have thermal oil heaters, so keeping the fuel warm. We don't have those so much now. I'm not an expert in this area, but fundamentally, there's still plenty of waste heat in the exhaust to use to drive an organic Rankine cycle. The trouble is the organic Rankine cycle efficiency is about 10%. And it depends how cold the seawater is. The colder the seawater, the better. And fundamentally, it's very difficult to make it work in terms of, because the reason why the ETI funded AVID is to reduce the cost price of an organic Rankine cycle. And that's what AVID are trying to do, make it, again, more commoditized, reduce the capex. The HT line, the charge air cooler and the jacket water, a lot more scope there for waste heat. I talked about on liners and other passenger vessels, you could use it for absorption chillers, which are they're not adapted fully for going to sea, but I believe there is potential there, and also, again, organic Rankine cycles. But they have been fitted as trials, but they've been taken off. And I think, it's the refrigerant in the organic Rankine cycle is expensive, and they're continually being changed over, and new technology refrigerant isn't cheap. So it is very challenging to make ORC affordable and cost effective.
Yeah, definitely makes sense. Got a question here asking, how much consideration have your projects given to ship kites, as they appear to be quite a low cost solution that can be easily integrated onto the vessels? They don't need a big refit period. Have you looked into those much? Okay,
we haven't modelled the kites in any detail, partly because Guy Sales and what the others, they came out, they were used, and then fundamentally they were not used. The savings they made, to my opinion, okay, but I understand the savings they made were not necessarily sufficient to recover the outlay. And also, when you think about it, where they are at the bow of the ship, they're getting all the green seas, so the equipment is very much under challenge. The fabric needs to be replaced every so often. And also, if it breaks, you've got to go forward and mend it right at the bow of the ship. and such like. So I think there's a number of reasons, you know, I don't know the true details, but I think the reason is that, you know, you're only going to get the benefit on a certain wind heading, and it, you know, they failed to do that. Having said that, SkySails are now very successful in terms of land-based projects where they're using these kites to as they reel in and out, or to make electricity as they, in a very clever way. So and there's also work in the UK and that, to that effect as well. So the reason why kites aren't actually on ships is that being at the bow, it's not a good place to have technology which has got to actually be actively winching in and out to keep the kite operating properly and doing its business, providing the thrust. And that's a tricky thing when you've got the worst possible situation for spray and green seas.
Yeah, that's definitely the case. It's not as simple as flying a kite at the beach and just tying it around your bollard at the front. They are, I think they're more high tech than people first think. Got another question asking, do you see these types of equipment being demountable in the future, so you can tailor them to the ship and swap them out on favourable passages?
I think, I mean, Flettner rotors are, the Flettner rotor that was added to the Maersk Pelican was fitted quite quickly. And so arguably, you know, they can be, and I think the Anemoy ones, you know, are also easily demountable. They're movable, so you can access the hatch covers. And I think, you know, so the answer is yes. And if a ship is doing a certain trading route back and forth, and then that's beneficial for wind, and then it goes and does a different route, and that isn't, then, you know, from what I've seen, it's quite straightforward to take them on and off. And indeed, what we need is this kind of commoditization, so that we have a large number of them. You can pop them on and off with a dockside crane, and fundamentally, and if the weather's too calm, it's summer in the northern hemisphere, it's not worth having them, because obviously if they're on there and they're not being used, arguably they're providing some drag. You know, so I can definitely see them being taken on and off. And you know, the wing sails aren't mature enough for that to be the case, but they're not, I wouldn't see them being particularly heavy. And also turbo sails, as you've seen, the ventifoils have been in containers and they can come on and off and such like. You know, the key thing is, of course, you still need all the integrated control and monitoring and such like on the ship. And the key thing with you know, these devices are providing thrust, so they've got to be integrated into the ship so that thrust is transmitted through to the ship structure in a safe way. No cracking, no other issues with deformation on hatch corners and things. So the key thing is, yes, you can bring them on and off, but the fact is they've got to be still integratable with the ship in a way that's you know, safe and reliable.
Yeah, it's similar to the problem we face in the naval industry quite often, where modular ideas are great once you can get the interfaces common against all the ships, and that's
right. And to be fair to class, I think since 2014, I think Lloyd's have had classification guidance for Flettner rotors. I'm sure DNV and ABS and the others have had the same, and so, you know, clearly safety. You don't want this device to jeopardize the safety of the ship. So, you know, you've got to have the weakest link so that you know that you're not going to damage hatch covers and other things and let water in big seas.
Yeah. I think we'll take our final question, which is, are there any kind of one-size-fits-all hydrodynamic devices that all ship owners should be considering retrofitting, or is each vessel very much its own individual cases? I know you mentioned propeller hub boss caps, which are quite a common. Yeah.
I mean, it is, and that's pretty low risk, isn't it? I mean, you know, so that would be, I think, you know, if they're all different. I mean, the more I look at it, the more I see them. I mean, you don't need to have a twisted rudder for every application. You don't need to have, you know, a kind of integrated propeller joined up to the rudder for all applications. And actually, you know, it is tremendously variable. I think the key thing is there's technologies. We've talked about air lubrication. You've got Silverstream Technologies in London and other suppliers, Mitsubishi air lubrication. That's been around for a long time. The Japanese did a lot of their initial research. And we know, you know, there's papers that are, in the Journal of Naval Engineering, which talk about how Maska was, you know, beneficial for ship's hulls. in the Royal Navy. But fundamentally, so air lubrication is good with wind devices as those ship speeds come down, as they have. So that would be my main answer, but I appreciate fitting air lubrication isn't always convenient and easy, but I think increasingly that's the case. And then you've got technology such as air coat coming through, where you might have a kind of permanent air layer on the hull using clever methods mimicking with biomimicry. So that I'm waiting to see that project come through with, it's a German-based project, I think, but the results so far don't seem to be that promising, but I'm always aware that projects start off with challenges and they find ways around them. But if you can keep the air layer next to the hull and reduce a lot of the viscous friction losses, I think that's going to be really good as well. And people will talk about hydrophobic films, which again have been talked about a long time. I think that those kind of things are also coming through in the next 5 to 10 years.
Thanks very much for that, John. I think we'll call the questions to a close there. Thank you very much for a really interesting lecture tonight. And yeah, there's certainly lots of interesting things on the horizon that we'll keep our eye out for. Thank you all for attending tonight. Our next lecture is on Monday, the 18th of January. It's titled Frigate Marine Integration De-risking. So hopefully see you all for that. Hopefully you should all receive a CPD certificate emailed out to the email address you registered to Eventbrite. We are aware that there has been some technical issues in the past month or two with the CPD certificates. Bear with us, we are trying to resolve them. But yeah, give it a few days. Hopefully a CPD certificate should appear in your email inbox. Thanks very much for joining us tonight, and have a Merry Christmas and a New Year, and we'll see you in January.